In this lecture, we'll introduce a new topic, which is rotation. We already have talked about it to a certain extent earlier when we talked about circular motion, but this is going to be a more in-depth review of a broad understanding which comes under the topic rotation. So, we already know the equation of kinematics. We know that if some object is moving in the x direction or on the x-axis, we know that the kinematics or the motion of the particle can be explained using three equations. And if we remember it properly, they were Vf equals Vi plus A Tf minus Ti, Vf squared equals Vi squared plus 2A xf minus xi, and xf equals xi plus half a tf minus ti squared. Now this was all about distance. So you have something moving on the x-axis. We also talked about cases when things were moving in direction, not just in the x-axis or the y-axis. Then what we did, we broke up into two parts. The problem was broken up into two parts. In the x direction was the one set of equation, and the y direction was the other set of equation. And these two set of equations were not really interfering with each other. But let's concentrate on this particular equations. Very similar to distance, there is another quantity that follows these three equations and behaves very much like distance. And if you give it a thought, you will find that it's angle. If you look at the watch, our clock, we have a second hand. Let's say it's a second hand of the clock, and this guy, well, it's moving clockwise, but let's say it moves in the anti-clockwise direction. There's something that is moving in the anti-clockwise or counterclockwise direction. So as you can see, this guy starts with certain angle, let's say theta I, and let's say it's the clock hand is moving, and we know as it moves, the angle increases, and when it reaches here, the angle is not 0, but instead it's 2 pi. So it has covered one rotation. This is one full rotation, 2 pi. Okay. Well, it can move in the other direction also. It can move faster, like the hour hand is moving slower, or the minute hand is moving a little faster than the hour hand, and the second hand is moving even faster than the minute hand. So it can move faster, it can increase the way it's moving. I mean, it can cover larger angles in smaller times. So it can do every single thing what distance can do. What can be done by a particle moving along the line can be done can be done by this minute hand, or whatever this thing is. It can cover angles, it can have angular velocities, and it can have angular accelerations. So it is just very much similar to distance or displacement. And because it is very much similar to x, we can rewrite these three equations for this guy. So we can say omega f equals omega I plus alpha Tf minus Ti, omega f squared equals omega I squared plus 2 alpha theta f minus theta I. Theta f equals theta I plus half alpha tf minus ti squared. You see there's a direct correspondence. Vf, which is the rate of change of distance or displacement, has been changed to omega f, which is the rate of change of angle. So this is sort of a velocity. This is the simple velocity, this is the angular velocity. This is how fast you travel the distance, this is how fast you travel the angle. And xi or xf has been replaced by theta I. That is, you start with some initial position xi, then you say no, you start with some initial angle theta I. Similarly, a has been replaced by alpha, which is the angular acceleration. Okay, but we know distance is nothing but distance from the x-axis. How is angle measured? What is the definition for measuring the angle? Well, the way angle is measured is, if you have a circle and you want to measure this angle, and let's say the length of this arc, this is an arc of a circle, is s, and the radius of the circle is r, then angle theta, which is this angle, is defined as s over r. That's the definition. And what are the units? As you can clearly see, we are dividing meter by meter, so so angle has no units, but people call it radians. Just for the sake of calling, it's called radian. Okay, and how much theta will be if you go from 0 and cover complete one circle? So if you cover complete circle, then theta is going to be, what is s? Well, s is the arc, and how much is the arc for one complete circle? It's the complete circle. So s for the complete circle we know is given by circumference, which is 2 pi r divided by r, and that gives us 2 pi, which means the angle of the whole circle is given by 2 pi. Okay, and other definitions: Vf is d theta over dt, alpha is I made a mistake, omega f is d theta over dt, and alpha is d, again I made a mistake, it's not omega f, it's just a general definition. Omega is d theta over dt is the general definition. Alpha is d omega over dt. So, and average omega is change in angle, change in theta, divided by change in time. Similarly, average alpha is change in omega over change in time. Very similar to what we did for average velocity, which was change in displacement divided by change in time, and for acceleration also change in velocity divided by change in time. And we also knew that if these changes went to smaller values, very small values, then this is how we write them, and average becomes instantaneous, right? So there's a direct correspondence between the distance and the angle. In fact, we can relate them. There's a relation between them, and how do we relate them? So they can be related just by understanding okay. So let's see if we can relate these guys, that is v with omega and we already know that r, we already have related r with theta when we said r is nothing but s theta, and s was r theta. We'll make it more clear, and a is alpha. So what do we have here? let's say we have a circle which is rotating. Then let's say you went from here to here, and because this guy is rotating, we know from circle it will have a velocity v, like a car, the wheel of a car is spinning. It will have a velocity v. Okay, let's say this small distance is ds, that is a small s, where we already have said s, used s as a symbol to express the arc, arc. Okay, so, and because of that we have a small angle d theta. So how is velocity going to be defined? Velocity is going to be defined as ds over dt, because this is the small distance the circle has traveled from here to here. Assuming that's a straight line, it's actually not a straight line, but because this thing is so small, you can assume it as a straight line, and that's what we do when we talk about differential things. This is the velocity of this guy here, and what is the angular velocity? We know angular velocity will be d theta over dt, right? And because s is r theta, these two should be related as v equals r omega, right? Because if it's not clear, I can just rewrite s as r theta divided by dt, and if r is constant, you can take it out, and this becomes d theta over dt, which is nothing but r omega. Similarly, we can also relate acceleration, which will actually give the same result. Okay, so these are the relations between these two sets of things. Let's talk two more things to complete our information base. We already have said that if this guy is moving in a circle, it suffers or experiences a centrifugal force. And if you remember properly, centrifugal force was given as v square, well, not force actually, well, let's keep it force only, mv square over r, where m is the mass of the object that is rotating. And centripetal acceleration, centrifugal acceleration, we already have talked about the difference between centripetal acceleration and centrifugal acceleration. Here we are talking about centrifugal acceleration. Is nothing but v square over r, just Newton's law is F equals ma. So this is F, and this is A, and this is m. Okay, we can rewrite this in terms of omega, because we know v is r omega squared divided by r, and that gives us r omega squared. So this is the centrifugal acceleration. These two are same. This is just sake of finding formulas, that's it. There's nothing new in it. Okay, let's talk about one more thing. If this guy, which is rotating here, now we know it has a centrifugal acceleration of v square over r, but let's say on top of centrifugal acceleration at certain time it has an angular acceleration also, right? It has an angular acceleration. By angular acceleration means its angle is also, its angular velocity is also increasing with time. Here we sort of, when we were talking about centrifugal acceleration, we assumed that velocity was constant, or angular velocity was constant. Both of them are related by this. So velocity is constant, angular velocity is constant. But let's say in this case, not only we have centrifugal acceleration, we also have angular acceleration. Then we know, we can redraw that we have actually two accelerations. One is outside, which is v squared over r when the velocity is v, and you can see this will keep increasing because velocity is going to keep increasing. And why velocity is going to keep increasing? Because omega is going to keep increasing. And why omega is going to keep increasing? Because there is alpha present. So there is an angular acceleration present that is going to increase the omega, which in turn will increase the velocity. Okay, so the other acceleration is going to be r alpha. Now, alpha is the angular acceleration, and this is going to be the linear acceleration. All these v a we are talking about is on the periphery or on the outskirts of the circle, somewhere here. So this guy here has velocity. This point here has a velocity and acceleration. It has v and a. So it's changing all the time. We know it's changing all the time. It's changing all the time because there is a centrifugal acceleration present. This centrifugal acceleration is dropping velocity, or the velocity is falling down toward the center all the time. So this is because of v square over r. But also there is an increase in the tangential acceleration. So this is radial acceleration. This is pointed radially, and this is tangential. Okay, if this is, so this is how your acceleration is, and you can simply write it as r, well, you can write it as v square over r comma r alpha at some velocity and some time, because velocity is increasing because of alpha. So this is only for a certain time. And what is going to be the magnitude? This is in Cartesian system. You can change to polar system by drawing by moving it to the Cartesian system, which you know the magnitude of a. So let's make a vector so that we differentiate with the magnitude is going to be, we already know how to do that, v square over r square plus r square alpha square. This is the acceleration. And angle theta is going to be tan inverse r alpha over v square over r, which is same as tan inverse alpha r square divided by v square. Right, this is the angle. So this covers a lot of small points, and they'll certainly be used in problems. We'll discuss some examples to make things clear.